Ratin with the channel. Today we are discussing the numerical, basically a graphical numerical on resilience and toughness. So before going into the problem, we should know, or I hope many of you know about what do you mean by hardness, what do you mean by toughness, what do you mean by resilience. So let me clear those who don't know or have some doubts. Toughness is the property of the material which enables it to absorb energy without fracture. So this part is very important. That means without fracture, or you can also say until fracture. Until fracture, okay? So just the point before fracture, whatever the material absorbs energy just when it is strained. Actually, suppose the material has been strained and it so eventually it will break down, right? It means it will go for fracture. So until fracture, that toughness is that property which enables it to absorb that much amount of energy. Okay. So then next, resilience is the ability of the material to absorb energy in the elastic region. So see, both are the ability of the material to absorb energy, toughness and resilience, but it is until the fracture point for toughness. And for resilience, it is the elastic region. So that is the difference. So coming back to our problem, in y-axis, it has been given the stress in megapascal MPa. And in the x-axis it is the strain, and strain has no unit, you know that, right? So, or mm by mm, that is no unit. So in this graph, if you see, let me put here 0. Okay, so you have to find out first resilience. To find out resilience, see, the question has been asked to find the resilience and toughness. You need Newton meter per meter cube. Okay, let me check again. Yeah, it's Newton meter per meter cube. Okay, so what to do now? How to find out? Since it is the resilience is the property of the material to absorb energy until elastic point. Okay, if you see the stress strain graph, and until here, let me call this point as A and this point as B. It is almost proportional. See, stress is directly proportional to strain. This portion, okay, from O to A. So we can consider the point A as elastic point, after which there is a change in the graph. See, okay, for simplicity purpose, I guess they have given the question. It is not exactly straight line, but we'll consider this as a straight line, OA and AB. Okay, so and B is our fracture point, or you can say breakdown point. Okay, so what happens? So but for brittle material, you can think of like this, but generally the graph doesn't go that much straight. If you do stress strain analysis to find out the elongation or the strength of the material, okay, using UTM, that is universal testing machine, so you will see in your BTech classes or in MTech, in manufacturing labs and all, you will see the graph is not that straight. Okay, that is a different thing you will learn in your lab classes. For now, let's find out the resilience. So now, how to find the resilience? So resilience, you remember, until the elastic point. So resilience will be this. See, let me go back to until this point, this graph. Are you getting my point? So OA, let me point this B and this point be C. So triangle OAC, this part of the it is the graph that is under this OA part, or you can say the triangle OAC, which seems, because this is a straight line, right, or a perpendicular line, I mean. So it looks like a right angle triangle. So we can simply find the area under the graph, that is the area of that right angle triangle. So it will be nothing but, let me put it in this way, half into base is OC, I guess, yeah, and that is O, and the altitude is, let me check again, OC is the base and AC is the altitude or height. So half. And what is OC now? If you try to find out, OC is from O to 0.004. So in x-axis it is 0.004. And AC, if you see, it is this 70 mark. Okay, from AC, the entire length of AC or the height of AC is 70. So if we find out using this, so it will be like, let me put it in this way, let me clarify the 1000, there will be 3 zeros, right? Yeah, into 70. So it will be 2, yeah, it will be 0, 0 gone, it will be 14 by 100. So if you see, it is in megapascal, so this means you have 10 to the power 6 with you. Whatever the stress value you are taking has, so you can simply multiply, that is 70 to 10 to the power 6, 70 to 10 to the power 6. So 10 to the power 6. So if 2 zeros are gone, I mean 100 is gone, let me put in this way, it will be 10 to the power 4, right? So gone, so it will be 10 to the 14 into 10 to the power 4 Newton meter per meter cube. So this is the resilience. I hope you have got the point. So we have find out the resilience until the point elastic point, okay, where the graph remains proportionate. The stress is directly proportional to strain. I hope you have learned the Hooke's law. From that you can say this thing. Now you have to find the toughness. So how to find the toughness? You have to consider the entire graph, okay. So the entire graph will be including this triangle OA, triangle OAC, area of the triangle OAC plus area of the trapezium AC, let me put this point as D, ACDB, the entire triangle, okay. Sorry, that is the trapezium. So you have to consider the entire trapezium, so the entire length, the first shade, that is the first triangle, and the entire trapezium to find out the toughness. So you have to add up both the things. So let me write here also, to find out the toughness, what you need to do, toughness, yeah, the toughness will be equal to area of triangle OAC, right triangle, okay, and area of trapezium AC, it was, let me name it, let me look into it, it is ACDB, okay, ACDB. So ACDB, so first you know the area of the triangle, that is 14, okay, into 10 to the power 4. It is already being known, found, right? The area of the triangle. Now to find out the area of the trapezium, you know the area is half. If you remember half, I hope you remember, half into the addition of the two sides or subtraction. If you remember, please try to recollect. We will use that formula. Okay, I will tell you a shortcut to find out, but definitely we will use this thing. See, let me go back. This AC, this entire AC. Okay, this entire AC are the two parallel sides and BD. See, this AC and BD are two parallel sides. So sum of the parallel side into the distance. The distance is this. This is the distance. I hope you got it. This is the distance, that is the CD. So half into AC plus BD, bracket, open bracket close, into the length between the two parallel lines, that is the CD. Okay, so we have to go by this way. Let me clear this so that there is no confusion with the diagram. Okay, so it is half into AC plus BD into CD. So 14 into 10 to the power 4, half into your AC and BD is nothing but, if you go on, it is 70 plus 120, and into 10 to the power 6 is there because it is in megapascal. Okay, don't forget that. And your CD is, if you go, I will show you the how I have got this. Let me write it first. It is 0.012 minus 0.004. Yes. How I have found CD equal to this, and let me go back, and trapezium starts from this point. Let me take in color, you'll see now. Okay, and this point. Your trapezium starts from C and ends at D, right? Let me put it this way, it will be much more clearer. So you have to, to find out CD, what you can do OD minus OC. So that's why the OD is 0.012 and OC is 0.004. That will give you what? That will give you CD. I hope you are clear now. So CD is clear, and AC is 70. See, this is the 70 line. I hope you can see this, right? And that thing, your BD is nothing but this 120 line. So that is 120 plus 70 into, if you see, into the subtraction to find out the CD. 0.012 minus 0.004. So let me find this into 10 to the power 4 plus half into 120 plus it is 190, I guess, yeah, 190 into 10 to the power 6, and this will be 0.008. yes, after subtracting. So let me go back to the black color. Okay, 14 into 10 to the power 4 plus half into, it will be like, yeah, it is 95 if I subtract this two, into 10 to the power 6, yeah, it is 8 by again 1000. So let me be clear with it. It will be 14 into 10 to the power 4. Okay, 95 into 10 to the power 3. Let me keep it as 10 to the power 3. Okay, so 760. So it will be, let me put it in this way. Let me be clear with this. Yeah, so it is 95. So 760 into 10 to the power 3. So we can make this as 10 to the power 4, right? 10 to the power 4 plus it is 76 into 10 to the power 4. So 10 to the power 4, 10 to the power 4, if we take common, so 14 plus 76 is 90. Okay, 90 into 10 to the power 4. So this is your, therefore this is your toughness. Okay, so you can write it as Newton meter per meter cube. Okay, so this is your toughness. So I hope you are clear with the toughness and the resilience. So we have found this until fracture. Do remember. Okay, toughness you have to find until the fracture. So we have, with the help of graph, we have done this. So that's why I have said earlier that it is a graphical numerical based on graph, or graphical numerical. So it is until elastic point. Your resilience is until elastic point. So kindly remember this. I hope you are clear. In the next video we will discuss somewhat more. with some other numericals. Till then, do subscribe the channel please, so it will motivate me and your mind so that you can learn better. Thank you. Bye bye.